All right. So double replacement reactions, we're going to exchange ions. And what you need to do is you need to look and see when you're doing these, what is your cation and what is your anion. And then here, cation, anion. And what I usually tell people to do is write the cations in the same spot again. So the calcium lead, I'm going to put the calcium here. Then I put the plus sign. Then I write in my hydrogen over here. And then we switch their partners. Okay? So calcium on this side is going to go with this anion, and hydrogen is going to go with this anion. And then that makes water. All right? But we need to make sure that the reaction is actually going to run. And that's where this chart is going to help you. Okay? This is called a solubility chart. So you need to get used to kind of reading that. And the solubility chart looks like this. Let me try to minimize that a little bit so we can work with it. Your cations are along the side, and your anions are across the top. And down at the bottom, there's kind of a key that tells you what these letters mean. Okay? If it says S, that stands for soluble, but I want you to think of that as aqueous. Okay? And on your phase accountability, you're going to write AQ. If it says slightly soluble or not soluble at all, you're going to consider those solids. So for the purposes of your equation, you're going to write an S in there. Sorry, I don't know why this is being mean. Okay. So you can see here that we've got different phases that are written in. Okay, everybody go with that? If both of our products end up being aqueous, then nothing has changed. And so we don't have a reaction that actually happened. And so that's why you have to check this solubility chart. And I'll kind of explain that as we go through the examples here about why that's the case. So if you end up with two aqueous, you don't end up with any kind of reaction. Okay, so if no product forms, so nothing changes, if it's aqueous on this side and everything's aqueous on this side, then nothing's happened. Let me insert an extra slide here, and I will explain to you why that's the case, okay? So I don't want to do that because I want to still have my colors for my markers. Draw. Okay. So if I had, for example, sodium chloride and potassium nitrate, okay? We can assume when we start out that, and don't even look them up, just go ahead and write down AQ here and AQ here, because they should always be aqueous to start with, okay? I'm going to write down my cation first. I'm going to write down my other cation, and then I'm going to swap partners. Okay, the chlorine is going to go with the potassium, and the nitrate is going to go with the sodium. I need to make sure that my charges are balanced. This is a +1, this is a -1, so that's all balanced. +1, -1, that's all balanced. Then I need to go to my solubility chart. I need to look these up. Okay, so on my solubility chart, I have formed potassium chloride. So I'm going to find my potassium here, and I'm going to find my chlorine. And when I do, see where that says an S here? That S stands for soluble. And what do you write down on your equation? You're going to write down AQ there. Oops, I put that on the wrong one. Sorry. It was supposed to be the potassium chloride. So I'm going to write down AQ here. And then I need to look up sodium nitrate. So I'm going to find my sodium, and I'm going to find nitrate on here, and I'm going to see that that also gives me an S. So that means that that one is also aqueous. If that's the case, then we actually don't have a reaction. And let me explain to you why. What this aqueous means is that if we have a beaker, okay, and we put this in, this is salt, like salt water, like in the ocean, okay? If I put that in water, it's going to break apart into these different ions, okay? And then I'm going to have some ions of potassium floating around and some ions of the nitrate floating around. If I go over here, okay, and I go to my product side, these all remain aqueous. So everything's still going to be floating around just like it was over here. Nothing's changed, okay? We've swapped partners on paper, but that's it, okay? In the beaker of water, nothing has changed. And so because of that, we consider this a no reaction because there's nothing that's taken place. That makes sense? All right. So let me go through kind of a reaction where we see that happening. So here's the first one. Let's go through this one. I'm going to write down my cation. I'm going to write down my second cation. Then I'm going to swap partners. This OH is going to go over here to here. And that's actually H2O, right? Because HOH would be H2O. And then this is going to come over here, which is the sulfate. Now, this has a charge of +1. This has a charge of -2. So I need to make sure that I've got that formula balanced before I carry on. If water is one of your products, that is a liquid, that is going to make the reaction run. We need to look up on our solubility chart our potassium sulfate to see what we're going to label that. So I'm going to find my potassium. I'm going to go over here to sulfate, and I see that that's an S. That means that it's going to get written down and recorded as AQ. But because the water was formed, that means that we are going to have a reaction. Okay? Then I need to balance my equation. All right? So over here, I have 2 potassiums. I need to get 2 potassiums over here, which means that that potassium is now going to be a 2 and the OH is going to be a 2. Then on this side, I need to get my H's to a 2 and my OH's to a 2. So if I put a 2 there, that takes those up and that gets that balanced. All right, makes sense? Everybody good? We're just swapping partners. All right, let's try the next one here. We've got iron and hydrochloric acid. So I've got my iron. I'm going to put him in his spot. I'm going to put hydrogen here, and then we're going to swap partners. Now, the problem is that they didn't tell us what type of iron this was. We need to figure out the oxidation of this iron before we can actually put it together with the chlorine properly. I know that sulfur is a -2, So what does that mean iron has to be? It's a +2. Good. Okay? Because there's no subscripts here. If this is a -2, this has to be a +2. So when I come over here, this is a +2. My chlorine is a -1. I've got to have 2 of those chlorine to make that work. Then I'm going to put an S here. And that ends up being, this is a +1, this is a -2. So I've got to have a 2 down here. All right. Now this is an acid. And on our chart over here, we don't have any acids listed. So I want you to write down in this section over here that all acids are aqueous. Okay. By the very nature of what an acid is, which you guys have not learned exactly what that is yet, we'll get there at the end of the year. By the very nature of an acid, it has to be aqueous. Okay. So I already know that my H2S is aqueous. I need to find that iron chloride on here. Okay. And there's different types of iron here. There's 2 different types. We decided that we were dealing with iron 2, and I need to go over to the chlorine, and it's an S. Okay. So if that's an S, that means what? That means that this is aqueous and this is aqueous. So what does that tell us about this equation? No reaction, yeah. And the beauty of a no reaction is, well, we don't have to balance that sucker. Not that this would be hard to balance, but all right. Let's go to the next one. Next one, we have sodium. And we've got hydrogen. My sodium is going to go together with my SO4. This is a +1. This is a -2. And then my hydrogen is going to go together with my chlorine. +1, -1. So this guy's already balanced. This, I need a 2 here. Okay. This is an acid, so we already know that it is aqueous. Don't need to look that up. But this one, sodium sulfate, we do need to look up. So I'm going to find my sodium here. And I'm going to go over to sulfate. And I see that it has an S here. So what do I record here for my phase if that's an S? Huh? Aqueous, yeah. And did you write down on your chart aqueous down there at the bottom what S means? That S means that we are aqueous. Did you write this down? Okay, so that's your key down here. So if you see an S, you know that that's aqueous. All right, both of these are aqueous, so that means no reaction. And the beauty is we don't have to balance. All right. Now, this is going to end up with a special case. So let's go through this one together again. I'm going to have my silver here. Why did I write aluminum down? Sorry. Let's try that again. I've got my silver here, and I've got my hydrogen. Then I'm going to swap partners. My chlorine is going to go over with my silver, and my hydrogen is going to go together with my carbonate. And then we need to balance this formula. So how many hydrogens am I going to need here? 2. Okay. Here, this is a +1, -1, so we're good. So let's go over to our chart. We need to look these things up. Okay. All right. So all acids are aqueous, but this is a special acid. We have 2 special acids, and these are listed at the bottom of that solubility chart. One of the acids is this, and you can see that this is the one that's on there, okay? When this acid forms, it automatically, like that, goes through a decomposition reaction where it forms water and CO2. So when you see this guy showing up, you actually have to erase H2CO3, and in its place, you write in H2O plus CO2. And because this is H2O, that's a liquid, and because this is a gas, we automatically know that this is going to run. We still need to go back and we need to check and see if silver chloride is also a solid or if it's aqueous. So I'm going to find silver chloride on here. Silver chloride comes in right here. So when I go back, I'm going to write a solid in for this. And then I need to balance my equation. I think that might have it done. Got 2 chlorine, got 2 hydrogen, got 1 carbon, and I've got 2 oxygens here and 1 here for a total of 3. So yeah, I'm balanced. Okay. Any of your other equations that I've taught you up until now, you don't have to write these phases in for your products, but when it comes to double replacements, you do, because it determines whether the reaction is actually going to run or not. Good. That's just kind of a flow chart. It's identifying. Okay, that's aqueous stuff. That's going to get into our net ionics. So when you go to your packet, there is the next assignment, I think, is 9-7. Okay, so that's what you're going to work on today. And then do you have a 9-8? I don't remember if there's a 9-8 in there, if that's net ionics or not. Okay. So for that one, you'll probably have to tune in tomorrow's video for that. Okay. How comfortable do you feel with these on a scale of 1 to 10? 8? 7? Okay. All right. So we'll see, how things go tomorrow with the kids that come in. If I have to like slow down to catch them back up, or that'll determine whether you get more net ionics tomorrow or not. But you can spend your time now working